again let us start with some point x star. Let us see what are the possible choices, right. So, now we want to understand how del of f of x star and del of g of x star should be related. Of course, you can pause and think here to see how these two should be related such that there is no descent direction, which is also feasible. Let me go ahead and explain, take a different configuration for the gradients and see if that works. Let us say if I took del f of x star and del g of x star to point in the same direction. Let us see what happens then. This, let us say this is del f of x star, and let del g of x star point in the same direction, maybe not the same length. I mean, the length does not really matter, right. So, it is only the direction that matters. Maybe that this is del g of x star, they are pointing the same direction. Now, is this a configuration where there is no descent direction which is also feasible? Again, let us go through the motions. So, how would we find this? We need to find out where are the descent directions and the feasible directions. In this case, again we will realize that this is the line where del f of x star transpose d equals 0, del g of x star transpose d equals 0, which means now if I look at this direction, this has the property that any direction here, which means that if I move here, 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 no matter where I move, I am guaranteed that d transpose del f of x star is less than 0 and d transpose del g of x star is also less than 0, right. So, both of these hold. Just to clarify, I might sometime use del f of x transpose d and sometimes d transpose del f of x star. Please do not get confused, these are the same things, right. A transpose b is same as b transpose a, and they are exactly the same numbers. Okay. So, now what does this mean? This means that if I move in the yellow direction, right. So, anywhere in the yellow space, if I end up in the yellow space, then I am it is both the descent direction and a feasible direction, which means that this is in some sense the worst possible configuration, because in this particular configuration every descent direction is also feasible, which is very bad, right. So, because then in some sense I have given you an x star which is really suboptimal x star, because I can move in any descent direction and I will still be feasible, right. So, at least in the previous case there were some directions where if you descended you may not be feasible, but all we need is a single direction to disprove my claim that x star is optimal. Here there are like a whole half space of directions, right. So, which means that x star again cannot be optimal for this configuration, for the configuration drawn above. Now, then is there even a configuration where it will indeed be optimal? Well, by now you should have guessed what is the configuration. It is not too hard to see that, maybe I will use a different page. So, it is not too hard to come up with the correct configuration now. Well, if you are at x star and your del f of x star points in this direction, but if your del g of x star, which could be of a different length potentially, points in the opposite direction, in the other words, del f of x star and del g of x star are anti-parallel, this is del g of x star, right. So, then where are the descent directions? Well, the descent directions are here, the yellow directions on this side of the purple line. So, these are the descent directions. On the other hand, because your del g of x star is pointing to the opposite side, your feasible directions are all going to be on the other side, right. So, these will be your feasible directions, which means that the moment I have found a direction where I can descend, it will not be feasible, because the feasible directions are on the other side, right. So, at least in this picture that is what that kind of tells us. Now, what can we say about this, right? So, essentially finally what we are saying is that a necessary condition for x star to be optimal is the following, right? So, the necessary conditions, this is not a sufficient condition, the necessary condition for optimality of x star is that these del of f of x star and del of g of x star should be, anti-parallel. How can I make it precise in a simple formula? Well, I can say that del f of x star equals sum minus lambda times del g of x star, where this lambda is a positive scalar. Right. So, there exists some positive scalar lambda such that del f of x star is not exactly minus del g of x star, this lengths could be different, and that the length, I mean it's the direction the same, but the length could be different, and so you have a scaling factor here which is given by lambda. Now, this is the condition that one would want to check. This is a necessary condition for optimality of x star for a constraint optimization problem. Great. So, remember our problem was minimize over x f of x such that g of x is less than or equal to 0. Okay, good. So, this is where we have reached. Now, let me also quickly try and do what happens when you have minimize over x f of x such that g of x equals to 0, right. So, this is like an equality constraint. Now, what changes if you have a equality constraint? One can ask that question. So, we can go over the same kind of argument to see when there will be a descent direction which is also feasible. But we just have to be careful where the feasible directions are, right. This is again an intuitive picture. So, you can again say that if let us say del f of x star was pointing in particular direction, let us say in this particular direction, nothing changes with respect to f, because nothing has changed in the problem with respect to f, only the g has changed. So, the descent directions will still be here. This is still the descent of I mean these are the directions where you can descend, right. So, T transpose del f of x star is less than 0 or descent directions. Now, the question is, where are the directions where you have feasibility, right. So, let us say you start with the g of x star which is kind of 0, which is feasible, and now you go to take a very small step, which is you go to g of x star plus some eta times d, where eta is really small. We know Taylor series would say that this is approximately g of x star plus eta d transpose del g of x star. Now, if this also has to be feasible, well, this is also 0, right. So, this is 0 plus eta times d transpose del g of x star. So, this is again an intuitive picture saying that if this condition has to hold, then it is like saying that we want to move along the direction d such that which makes the dot product of 0 with the gradient with respect to g, right. So, which means that let us say if the gradient with respect to g was pointing again in this direction, del g of x star, well, for a small enough step you want to kind of move in a direction which is making a dot product of 0 with del g of x star. Where are those? They are here, right. So, this exactly on this line you will have del g of x star equals 0. Now, on this line we can move anywhere, and then the descent directions are all the yellow region, which are a whole half space. Now, is this configuration optimal? Of course, it is not optimal, because I can always move in a small direction which is making a dot product of 0 with the gradient, but then it will take me to a descent direction. So, this is not an optimal configuration. So, now we again ask the question, where is the optimal configuration? Well, now the situation is slightly different from earlier because we do not have a whole half space of feasible regions, but then only like a line. Now, if you have again del f of x star, now if let us say del g of x star was opposite direction like how we had earlier for the case where you had an inequality constraints, let us say this was del g of x star, well as before. So, this is the feasible region, I am sorry, this is the descent region, and the feasible region is on the orange line, right. So, the feasible, sorry, should I use a different color. So, this is T transpose del g of x star 0, the orange line, whereas the yellow line is the descent direction, which means that the moment I move along the yellow direction, I kind of go away from the orange line, right. So, I cannot move in the orange line and still descend, that is the point, right. So, if I move in this direction, it is also going to make a dot product of, sorry, also going to make a dot product of 0 with del of f. So, it is not really a descent direction, only when there is a when it is strictly less than 0, it becomes a descent direction, which means that on the line I can still move and I will not be able to descend, right. So, which means that this is a configuration which is in fact an okay configuration, right. So, which is exactly the same configuration that we had for an inequality constraint, but then additionally there is one other configuration which will also work in the equality case, which did not work in the inequality case, which is when not only the case when del of f of x star and del of g of x star are anti-parallel, but even in the case when they are actually parallel, right. So, even if they are parallel, let us say del g of x star. Now, if I still ask the same question, well, this is the case where this is d transpose del g of x star is 0, it does not change, right. Just because we are making del g of x star, we are flipping it from the anti-parallel to parallel, the line which makes a dot product of 0, right. So, the line which is perpendicular remains exactly the same, and so you can potentially have this configuration as well, where you will still will not be able to find a descent direction which is also feasible, right. So, that is the difference between the inequality constraint and the equality constraint. So, this is, let me make it clear, this is del of d transpose del f of x star is less than 0. So, which means that the moment we come out of this line, we may descend, but then we might not be feasible, right. So, that is the whole point. So, which means that there are two cases now, either del of g of x star is parallel or it is anti-parallel, right. So, now how do we formalize that? We can formalize that again in exactly the same way as we did before. We can say that del f of x star equals minus lambda del g of x star. This is what we had earlier, and then we said that because we only allowed anti-parallel in the previous case, we constrained lambda to be positive. Here, because we are allowing it to be either positive or negative, there is no constraint on the sign of lambda. We are simply going to say that lambda can be any arbitrary scalar, right. So, it can be anything basically, right. So, non-zero arbitrary scalar. So, that as long as this condition is satisfied, then it is a necessary condition for the constraint optimization problem with an equality constraint. Good. So, now this lambda has a special name and it is named after Lagrange, a famous scientist, a mathematician, and it is called as Lagrange multiplier. Now, what have we said so far, right? So, all we have said so far is we started with an unconstrained problem. We said that gradient descent would work there, but then the moment you introduce constraint, gradient descent may not work, and then we asked when would an x star be optimal, what is the necessary condition, and the necessary condition that we have come up with is that del f of x star should be minus lambda del g of x star, and in the case of an equality constraint, lambda can be anything. does not have any constraint, but then in the case of inequality, lambda has to be exactly 0. Now the question is, fine, so this is an optimality constraint, but then how do I use this to actually solve a problem, right? So how do I finally get the answer by using this equation, right? So that is a question that we want to answer, for which we will see an example, a specific example with an equality constraint where you can use the method of Lagrange multipliers to solve the problem, and that is what we will see next.